Hello everyone, in this video we're going to talk about implementing a queue using an array. In my other videos I explained implementing a queue using a linked list, which is another kind of data structure. However, in this video I'm going to see what are the challenges and complexities related to implementing a queue using an array which has a fixed size in general. So just to review the concept of the queue is a data structure which we're inserting a data from one end and we're removing data from the other end. So here's an example of a queue front, which is the front of the queue where we are removing the item from, and end is where we're inserting the item from that side. As we all know, queue is a first in, first out, or a FIFO data structure, means the first item to be which is inserted will be the first item to be removed. So when we're showing a queue, as you see on both sides of the queue are open, which means that both of the so the one is for the entering the data, so data will enter from this side and will be exited from the other side. So let's see that how we can implement a queue using an array. Similar to my other videos, I'm using a code very similar to the Java with skipping some details. So this is going to be the class which is generic, so it means that data can be from any type, and this time the data will be an array. So here, when we're implementing a queue using an array, we need to be careful because we're going to work with the indices of the array, which we call it the storage here. One option or one way of implementing a queue is always to keep the front index, or where the very first item is located, to be the index 0. In that scenario, we need to actually move or maybe shift items from the right side to the left. So I'm going to draw an example here to see that what does it mean to have the front index to be always 0. So here is a queue, and here is index 0 of the array 1, 2, 3, 4, and 5. So let's say this is our array with a length of, or the maximum capacity of 6. So if we have an item, let's say for example number 5 here, and then number 10, and some other numbers such as 15 or 20 or 25, then let's say we're going to dequeue, which is an operation in the queue, which means to remove the very first item. So removing the very first item at index 0, which is the front of queue, will create something like this. Number 5 will go away. So if you want to keep the front index to be 0, what we need to do, we need to shift every item from right to the left. That means that our dequeue operation will not be from the big O1, because we need to shift n items, and again n is the number of items in the queue to the very left. So as you see here is this is a case where we have a fixed front index. So if the front index always 0, we need to shift items to the left. So maybe that's not very ideal. In other words, what we can do, we can actually make the front index dynamic. It means that anytime that we are dequeuing some item from the end of the queue, from the very front of the queue, we can actually increase the front value, or actually update it, because not all the time is increased. So here, instead of like the shifting, so one way, so I'm going to write the scenarios way like the with fixed front index, and let's say front is always equal to 0. Then with this scenario, what we need to do, we need to shift all items of the queue to the left. That's the first one. The second scenario is that when we have a dynamic one. In this case, we need just to update the front index without fixed front index. Just we're updating the front index. So I'm going to write an example with the same one here. So 5, 10, and 15, and 20. So here, and draw the same example. So index 0, 1, 2, 3, 4, and 5. And here are the numbers again. We have number 10, 15, 20, and 25. So if I'm gonna dequeue, which will remove number 10, or the front index, which at first was index 0, will not be 0 anymore. So I don't need to shift. Indeed, number 10, when it's gone, I will increase front by 1, and front will be the index 1. So what's going to happen? So I need to increase front by 1. So front plus plus, or another word, front equal to front plus 1. So you might ask, so what if then the front index becomes the very last index? I mean index 5. So what's going to happen? In this case, if we remove the very last item, which is going to be here, then we're going to have an issue of not being able to insert a new or enqueue any new item into the the queue. So let's see that how it works. For example, if I had some other numbers such as 20, I think that was number 5. Let me just fix this one here, the example, just to have the same example. Here we had 5, so here was 5. Then we have a 10, so here's 10, 15, 20, and 25, and let's say we have number 30 here. So I'm going to see that what can be the problem with having a dynamic index if we only just increase the front by 1. So dequeuing for the first time will remove number 5, and front index, I'm going to just use F, will be equal to 1. After that, what's going to happen, if I call the dequeue one more time, so the dequeue will pop number 10, so I'm going to also have the number 10 will go away, and front index will point to this location, which is front will be equal to 2. So if I continue with that, so dequeue will return 15, and F will be equal to 3. Dequeue is going to give number 20, and F will be equal to 4. And dequeue again will return number 25, and F will be equal to 5. And this time when I dequeue, which will return number 30, F will be equal to 6, which is an invalid index. So that is invalid because the last index in this array is equal to 5. So here is actually a fix. So I explained this example to say that just increasing the front will not be like the final solution. So one thing is that we can actually have a circular like the queue, which that the front queue, after it becomes 5, next time instead of becoming 6, which does not exist, it can go back to the very front of the array, so front can be equal to 0. So to fix the problem then, instead of writing front equal to front plus 1, instead we are adding this one or modifying that to this front plus 1, and then we are taking the modulus operator and the modulus of the size or the length of or the maximum capacity of the queue, which in this case is 6. So 6 or the length, whatever is the like the length of the queue, will give us the proper front index. So when going back to this example I have here, after dequeuing number 30, what's going to happen? Front will be 5 plus 1, so 5 plus 1 is going to be 6, and then 6 modulus 6 will give me the answer 0. So what's going to happen? I'm going to just go here. The front index after is here will go back to the very beginning of the queue, and that's going to fix the problem of like the wasting like the memories or not being able to insert into the queue any longer. So just to summarize and going and writing the code together, here is the class again, the class queue with the details of implementation for the Dequeue and the Enqueue methods. So class queue. So we're having an array of a generic type, and then what we can do for the Enqueue method with the data of type T, we're gonna make sure that like the data will be stored at, so I'm gonna keep also the indices, so front, which is an integer, and also the end, which gonna be the index. So the front and end are the two indices that I need in order to access the very first of the queue and the very last item of the queue. So storage at location front, excuse me, is going to be actually storage at location end, where is the last index, because we'll always insert at the very last. Storage location end will be this data we have. For sure, we need to increase the end. So again, that can be a problem if you're enqueuing at the very end. So there might be not any more index places here. So or like the overflowing or going out of the index. So same thing that we did here, that we use the modulus, we're going to use the same thing here for the enqueue. So the end index actually will be equal to end plus 1, and then the modulus of the length of the storage. So storage, the length, or in other words, what is the capacity of like our queue. So again, this n plus 1 is for the cases that we need we have used the very last index of the queue, which is for example here. So we inserted for example number 5 here, and now end, instead of to pointing to the some places here that which not exist, actually will go and be the very first one. We're going to see that even this approach might cause some issues, but let's just finish this one, and then we can discuss that one also as well. So here's the enqueue, and the Dequeue method will, again, we're going to return the data from the type T. We're going to return the data, so storage at location front. Let's just have it like some temporary variable such as data, and then we're going to increase the data by 1, but take the modulus of the front plus 1, storage the length. And modulus, maybe I have not mentioned that, the modulus will take the remainder of dividing front plus 1 by storage the length. And at the end, we'll just simply return the data that we just stored. So as you see here, this is almost good, but we won't have like the one tiny issue is that when the front and end actually become equal to each other. And I'm going to show with an example that what's going to when this can happen and how actually we can avoid that. So, but before that, I'm going to talk about the time complexity of the Enqueue and Dequeue method. As you see here, the number of operations, the main operation in both Enqueue and Dequeue method. In this implementation, when the front and end, both of them are dynamic, is from the big of 1. However, again, if we are using the fixed front, because we need to shift items from the right to the left, as you see here. Then the time complexity for the Enqueue method will be from the big O of n. And with the fixed front value, still we can keep the front n to be dynamic, and we can keep the Dequeue method to be big O of 1. So going to that issue that I said, and I'm going to just draw an example and see that why this can happen and how we can avoid that or fix that. Look at this example here. I'm going to maybe use the smaller queue just to go faster over this example here. So let's say that we are enqueuing number 5, which will put the front to be still 0, but we'll change the end to be 1. So here we have front, and here's our end. So here is going to be number 5. One thing that like the Enqueue, maybe what I had to do, maybe just to write storage at location. Yeah. So after that, and this is still n will be 1, so it's here. But in the Enqueue, maybe we need just to write n minus 1. So I just want to n minus 1, just moment to make sure that our implementation is accurate enough. So n minus 1. So, and then after that, we need to increase actually end by 1. So just to make sure that we're going to the proper location. So n is going to be 1, and the front is here is going to be equal to 0. Let's say we are enqueuing another item. So let's say, for example, 10. So front is still 0, but end will be equal to 2. So number 10 is here, but end will go to here. And then let's say we are enqueuing another number, let's say 20. So front is still 0, but end will be equal to 3. So here is number 20, and end will point to here. And now let's say we're going to enqueue another item, which is 25, and then front will be still 0, but because based on that formula we have, end will be equal to 0. So 25. And now front and end, both of them are equal to each other. So far so good, no problem here. The problem is if we want to enqueue another item. For example, if we want to enqueue number 30 or 35, then it's actually going to override like the number 5, and we have not removed number 5 yet. So as you see here, when the front and end are equal to each other, and when the size of the queue is also full, we need to just check that. So anytime that we're enqueuing an item or we're dequeuing an item, we need just to make sure that the front and end, if they are equal to each other, the queue is not full, just to override like the data that already exists. And again, it just can be done with a small check when we are doing the enqueue process or dequeue process, which is if the like the size of the queue is equal to the capacity of the array. So as you see here, with this like the implementation of the queue, we have like the more challenges, which is about like again just keeping the indices front and end, and having like the difficulties with keeping the front index separated, and making sure that we don't need to shift, and also for a better performance, we need to make the queue a circular one rather than having a fixed one, because we need to deal with the shift problem, which gonna increase the time complexity of the enqueue or the dequeue operations. So you can again watch my other videos about implementing a queue by a linked list, which as we discussed, both enqueue and dequeue operations had the time complexity of big O of 1, and it was easier to implement that. Implementing a queue using an array can have like this advantage of like the just fixing the size of the queue 8 of times, saying that that's going to be the maximum size that we're going to assign for the queue. However, we can still with the linked list, we can manage like the memory and limit the number of items that we're going to have in the queue.